Next chapter, reaction rates and reversible reactions. Now, in our everyday life, we encounter reactions that we can consider to be very fast, like combustion reactions. We also see reactions that are so slow that sometimes we don't even realize they are happening, like rusting. During chemical reactions, reactants are converted into products. So over time, reactants decrease while the products increase. The rate of a reaction tells us how rapidly the products are formed or how rapidly the reactants are consumed. So mathematically, the rate of a reaction is equal to the amount of product formed over time or the amount of reactants used over time. So if we want to know the rate of a reaction, we can either measure how much the reactants disappear per unit time or how much product is formed per unit time. There are a couple of experiments we can perform to measure the rate of a reaction, depending on what we can observe during the reaction that we can easily measure. For example, we can measure the volume of a gas produced in a reaction at regular time intervals. We could, for example, note the readings on the gas syringe every 5 seconds after the reaction started. Let's say we take a conical flask and add hydrogen peroxide to it. We then add a spoonful of manganese 4 oxide as a catalyst. We fit the flask with a syringe. As the reaction proceeds, oxygen gas is produced and collects in the syringe. We measure the volume of oxygen produced after every 10 seconds. If we plot a graph of volume against time, this is the curve that we will obtain. From this graph, we can see that initially, a large volume of gas is produced within a short time, so the rate of reaction is high in the beginning. The rate then slows down over time as the reactants get depleted. Less and less gas is produced per unit time. A similar experiment can be performed in which we measure the decrease in mass of the reactants at regular time intervals as a gas that is produced is lost into the atmosphere. For example, the reaction between hydrochloric acid and calcium carbonate can be measured quantitatively. It is performed in a conical flask on a weighing scale. A spoonful of calcium carbonate is added to a conical flask containing dilute hydrochloric acid. The readings on the scale is recorded every 10 seconds until all the calcium carbonate disappears. If we plot a graph of mass against time, we obtain this curve. From this curve, we can see that the rate of disappearance of calcium carbonate is faster at the beginning but slows down as the reaction progresses. We could also measure the time taken for a color change to occur or for a solution to be opaque. For example, the rate of reaction between sodium thiosulfate and dilute hydrochloric acid can be measured by the rate of formation of sulfur, which makes the colorless reaction mixture go cloudy. A white sheet of paper with a black cross is taken. A conical flask is placed on it and dilute hydrochloric acid added. And then sodium thiosulfate is added to the acid. Immediately a stop clock is started. As the reaction proceeds, the flask gets more and more cloudy and the visibility of the cross diminishes. This is because the concentration of sulfur increases over time. So in this case, we measure the rate of formation qualitatively rather than quantitatively. So how does the rate of a reaction change as the reaction proceeds? Let's take a reaction of zinc granules with hydrochloric acid. It produces zinc chloride and hydrogen gas. We shall measure the volume of hydrogen gas produced at 10 seconds intervals. At first, we see that the rate of production of hydrogen is faster. But as the reaction proceeds, the volume of hydrogen produced per given time interval is lesser and lesser. If we plot a graph of volume of hydrogen against time, we shall obtain this kind of a graph. The rate of a reaction is highest at the beginning and slows down as the reaction proceeds and eventually stops. At the beginning, the concentration of the reactants is at its highest, but as more and more reactants are converted to products, the concentration of the reactants decreases and the reaction slows down. When one of the reactants is depleted, the reaction stops. We can calculate two values of the rate of reaction. First, the average rate. This is the average volume of the gas produced over a given time interval. For instance, the average rate of reaction between 20 to 30 seconds will be given by average rate is equal to V2 minus V1 over T2 minus T1. And secondly, the instantaneous rate of reaction. This is the rate of reaction at a given point, that is at an instant. For example, we would want to know the rate of reaction at point P. To do this, we find the gradient of the tangent to the curve at point P. So the instantaneous rate at P is equal to the gradient of line AB, which is equal to the change in volume over change in time. That is VB minus VA over TB minus TA. Next, collision theory and activation energy. Now, suppose we have a beaker of cold water and a beaker of hot water. When you add sugar cubes in them, the one with hot water will dissolve faster than the one in cold water. To explain the different rates of chemical reactions, Max Strauss and William Lewis came up with the collision theory in the early 1900s. The first postulate of the collision theory is that particles must collide with one another in order for them to react. Most particles will act like the billiard balls in a game of pool, and when they collide, they bounce off each other. The collision is not all that is needed in order for a reaction to occur. The particles must also collide with enough energy to break and form new bonds. The minimum energy required to kickstart a reaction is called the activation energy. Some reactions require very little, and some require more to get started. You can think of a reaction as trying to roll this ball through the green path. If we have enough energy to roll it uphill, it is going to roll down to the other side. In other words, the ball had some energy at the beginning, which is potential energy, and we lost some of that in the end, but the ball did not go there on its own. We had to put in some energy to get the motion started. So this initial energy is the activation energy. In terms of chemical reactions, the reactants are here and products on the other side, and this is an exothermic process. An endothermic process will look like this. If we don't have enough activation energy, the ball is not going to get over the hill. And that is exactly what happens during chemical reactions. This graph shows a hypothetical reaction between atoms A and a molecule containing atoms B and C. The activation energy, EA, is the amount of energy needed to get the reactants to the transition state in which bonds are broken and new bonds are formed. This transition state usually lasts for a fraction of a second. In this reaction, the products are molecules AB and the atom C. Because this is an exothermic reaction, some of the energy stored in the reactants is released. Often, activation energy can be a barrier that prevents chemical reactions from occurring. For example, if methane and oxygen are mixed together in the same container, they collide, but there is no reaction until a flame or a spark is added. To react, the molecules must collide with sufficient energy to break the oxygen-oxygen and carbon-hydrogen bonds so that new bonds can form. This additional energy is the activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide, but they lack sufficient energy to react. A flame supplies the activation energy that is needed. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies enough energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continuously colliding but lack sufficient energy to react. Heat from lightning supplies the activation energy to break the bonds, and new bonds form in an endothermic reaction that absorbs energy. Generally speaking, most reactions will occur faster when temperature is increased because temperature is the average kinetic energy of particles. With more kinetic energy, the particles move faster and collide more often with higher amount of energy. Now, for most reactions, there is still one more factor: orientation. Even if particles collide with sufficient speed, if they don't do it in the correct orientation, a reaction won't happen. In this reaction of nitrogen-1 oxide and ozone, the reaction did not occur because the oxygen of each molecule touched during the collision. The collision is said to be unsuccessful. But if the nitrogen touches the oxygen, a reaction occurs, making oxygen and nitrogen-4 oxide. This is a successful collision. So the three key ideas of the collision theory are that the particles must collide to react. They must have sufficient energy to break and make bonds, and they must collide in the correct orientation. Next, factors affecting the rate of chemical reactions. Now, we've said that a reaction occurs when the reacting particles collide in the right orientation with sufficient energy. Any factor that affects the frequency of successful collisions will affect the rate of a chemical reaction. Factors that affect the rate of a chemical reaction include concentration, temperature, surface area, catalyst, and light. Let's start with the effect of concentration. Now, we want to perform an experiment to compare the rates of reactions when we vary the concentration of one of the reactants. We saw that we can measure the rate of a reaction by measuring the amount of product formed per unit time. In this experiment, we will react dilute hydrochloric acid with sodium thiosulfate. We shall have a fixed concentration of hydrochloric acid, but we will vary the concentration of sodium thiosulfate. From this equation, the sulfur that is formed as a product makes the solution cloudy and therefore reduces the visibility. Our main idea is to measure the amount of time it takes for the solution to become completely cloudy. We take 10, 20, 30, 40 and 50 milliliters of 0.1 molar sodium thiosulfate in conical flask A, B, C, D, and E respectively. Then we prepare a table like this one so that we can do the dilutions. We measure 40 milliliters of distilled water. We pour this volume to the conical flask A. Now the total volume of the solution becomes 50 milliliters and the concentration drops from 0.1 molar to 0.02 molar. Next, we measure 30 milliliters of distilled water. We transfer it into conical flask B. The total volume of the solution will be 50 milliliters and the concentration drops to 0.04 molar from 0.1 molar. Now you get the drill. We add 20 milliliters of distilled water into conical flask C. The total volume becomes 50 milliliters and the concentration now becomes 0.06 molar. We add 10 milliliters of distilled water to D. Volume becomes 50 milliliters and the concentration is 0.08 molar. To the last flask, we don't dilute it. The volume remains 50 milliliters and the concentration is still 0.1 molar. So we have diluted the solution of sodium thiosulfate successively by adding water. We shall react each with 10 milliliters of 1 molar hydrochloric acid. Place the conical flask A on a white tile with a cross mark. Measure 10 milliliters of 1 molar hydrochloric acid with a measuring cylinder. Pour half of the acid into the conical flask and start a stopwatch. Shake the mixture and return the flask on the tile. Observe the solution in the conical flask from the top. The insoluble sulfur formed during the reaction gives a cloudy appearance, making the solution opaque. Stop the stopwatch as soon as the cross on the tile becomes invisible. Note the time taken and record it. Repeat the same with flasks B, C, D, and E, each time noting the time taken. Calculate the reciprocal of time, that is 1/T. Plot a graph of 1/T against the concentrations of sodium thiosulfate. We will obtain a straight line that indicates 1/T is proportional to the concentration of sodium thiosulfate. Remember, 1/T is equivalent to the rate of a reaction. That is, rate is equal to 1/time. And therefore, the rate of a reaction increases with increasing concentration of the reactant. What is the explanation for this? Again, recall that reactions occur when they are effective or successful collisions. A higher concentration of reactants means more particles per unit volume. The frequency of collisions therefore increases. This will also increase the frequency of successful collisions, and therefore the rate of a reaction is increased. Next is the effect of temperature. Now, let's study the reaction of oxalic acid with potassium manganate 7 in the presence of sulfuric acid. We take 0.5 grams of oxalic acid in a beaker and dissolve it in 20 milliliters of water. To this oxalic acid solution, we add 5 milliliters of dilute sulfuric acid. To this mixture, we add a few drops of potassium manganate 7 solution. The solution turns purple. Stir the solution with a glass rod for a while. The solution remains purple in color. In another beaker, we prepare oxalic acid solution as we did before. We add 5 milliliters of sulfuric acid to it. We heat the solution to about 60 to 80 degrees Celsius, and then we add a few drops of potassium manganate 7 solution. You will see that on stirring, the purple color of the solution disappears. So increasing the temperature increases the speed of reaction between oxalic acid and potassium manganate 7 in the presence of sulfuric acid. So generally, increasing the temperature increases the rate of a chemical reaction. We can depict this with a graph of rate of reaction against temperature. What is the explanation? Increasing temperature increases the kinetic energy of particles. They move more vigorously and with greater energy. This increases the number of successful collisions per unit time and hence increases the rate of reaction. Next is the effect of surface area. Let us perform an experiment. We have 3 beakers, each containing the same concentration of hydrochloric acid. And these black containers contain calcium carbonate. Here, calcium carbonate is in powder form. This one has medium-sized carbonate chips. And this one has fairly large pieces of calcium carbonate. So we will add each to the acid and observe if there is any difference in the rate of reaction. We start with the large pieces. You can see that the reaction is not very fast, but it's still fine. For the medium-sized, you can see that the reaction is much faster. And finally, for the powdered calcium carbonate, it is observed that the reaction is very fast compared with the other 2. And so as the surface area increases, the rate of reaction decreases. We can show this with a graph of rate of reaction against surface area. So what is the explanation? If the size of a reactant is smaller, the total surface area exposed to collision of particles is larger. The frequency of collisions will increase. This will increase the frequency of successful collisions and therefore increases the rate of reaction. Next, effect of catalysts. A catalyst is a substance that increases the rate of a reaction but remains unchanged in the end. The rate of decomposition of hydrogen peroxide in the presence of a catalyst can be compared with the rate in the absence of the catalyst. We take 2 conical flasks A and B and we add equal amounts of hydrogen peroxide to each one of them. A catalyst by the name manganese 4 oxide is added to flask A. Both A and B are fitted with syringes, ensuring they are airtight. As the reaction proceeds, the oxygen gas produced collects in the syringe. As you can see, the amount of oxygen liberated in A at any given time interval is larger than B. If we plotted graphs of the volume of oxygen against time, we will have these curves. So what is the explanation? A catalyst increases the rate of a reaction by lowering the activation energy. So particles do not require as much energy as when there was no catalyst. Notice from the graphs that the eventual amount of oxygen produced is the same in either cases. The difference is the rate at which they are produced, or rather the time taken to produce the same amount of oxygen when there is no catalyst and when there is a catalyst. Lastly is the effect of pressure. Now, pressure only affects reactions involving gaseous reactants and gaseous products. At a higher pressure, the same amount or number of gas particles will occupy a smaller volume. This will increase the frequency of collision of the particles. The frequency of successful collisions increase, and thus the reaction proceeds faster.